Welcome to the PetroPapers podcast. Say that 10 times fast. This is where you get your oil and gas intellectual stimulation by asking the technical questions. I'm your host, Yogesh Pradhan, and with me here today, I have Dr. Mark McClure, founder and CEO of ResFrac. Today, we're going to talk about URTEC 123, which the paper citation is in the description below. I'm going to talk a little bit about Mark before we take a deep dive into the paper. He's the co-founder and CEO of ResFrac and also served as an adjunct professor at Stanford University. He also served as an assistant professor at the University of Texas, Austin. Mark McClure has also received several awards, such as the Energy Influencer by the Young Professional SPE magazine, called The Way Ahead, as of 2021. In 2019, he was Hart Energy's 40 Under 40 recipient. And in 2019, he also earned the URTEC's Best Paper Award. Mark has earned his bachelor's degree in chemical engineering, master's degree in petroleum engineering, and a PhD in energy resources engineering, all from Stanford University. So welcome to the podcast.
Well, thanks. I'm excited to be here. Looking forward to talking about the paper.
Well, before we take a deep dive in the paper, I had a couple questions for you. First, what exactly does ResFrac do?
Yeah, we make a combined hydraulic fracturing and reservoir simulator. It's unique to take those two different types of software and put them together. Conventionally, frac simulators and reservoir simulators are different things. It's useful to put them together because a lot of processes like parent-child frac hits involve multi-phase flow and fracture mechanics and propagation and proppant transport and wellbore transport all at the same time. And so by taking all the relevant physics, solving all the relevant equations simultaneously in every time step, we get a more realistic answer. So we use that to help companies optimize well spacing, frac design, strategies to mitigate parent-child problems, geothermal, et cetera, et cetera. So it's a physics-based solution used for engineering and optimizing subsurface systems using fractures.
That's exciting to hear, especially the geothermal component and working in the geothermal space. The other question I wanted to ask you, since I invited you for this particular paper, is so we can reorient our viewers and listeners. Can you briefly talk about URTEC 123?
Yeah, so URTEC 123 is the outcome of a one-year collaborative industry study that we did with 7 operators. The operators all shared a diversity of DFITs that they had performed in a variety of formations. And we should define a DFIT. DFIT stands for Diagnostic Fracture Injection Test. It is a mini frac test where typically you'd inject around 10, 20, 30, and maybe up to 100 or sometimes hundreds of barrels of fluid, usually at the toe of the well. So it's after the well has been drilled, after the well has been cemented, et cetera, but it's before the full frac job. And so you use just clear water, not the frac fluid, just clear water, make a small fracture, and then you shut in. You monitor pressure over time, and there are 3 objectives to measure the stress, the permeability, and the pore pressure. So maybe decades ago, the idea of a mini frac test or an extended leakoff test would be to estimate only the stress. And also decades ago, you're usually in higher permeability rocks, so shut-in periods were pretty short. But in these DFITs, they're performed in shale. We want to get pore pressure, permeability, and stress. So the shut-in could be, I'd say on average, 1 week is the most common. Sometimes we get a month, sometimes we get a little less than a week, but pretty long shut-in that gives you a lot of data to estimate not just stress, but also reservoir parameters. So in this study, we got a lot of data from these operators. We had a quarterly meeting, a total of 5 meetings over 1 year, where we went through their data, went through all the modeling and the kind of procedure that we started putting together. And then what ResFrac's role is a DFIT is really something that inherently involves fracture mechanics and multi-phase flow, right? So a DFIT, you propagate a hydraulic fracture, then you shut in. The fracture walls have to contact, and the fracture walls in reality are not perfectly smooth, but rather there's a roughness in the fracture. So the asperities, the rough points in the fracture, they start to contact, and then the fracture kind of squeezes shut like a spring, a very stiff spring, and it gets stiffer and stiffer. At the same time, fluid is leaking off, and it's a multi-phase flow problem. So prior to a few years ago, DFITs had really been kind of analyzed in the field by looking at a so-called pre-closure solution and a so-called post-closure solution or after closure. So a pre-closure solution assumes that the walls are completely out of contact. And then an after closure solution assumes that the fracture closed a long time ago. And the after closure solutions were traditionally based on kind of conventional pressure transient analysis techniques. And the pre-closure solutions were based on kind of fracture mechanics solutions. So there was this big gap, the part where the fracture walls begin to touch. And in a pre-closure solution, often they were assuming Carter leakoff. Carter leakoff is great during a frac job, but it's only valid if the fluid pressure in the fracture is constant. And when we do a DFIT, we shut in. The whole point of the DFIT is pressure drops off dramatically and asymptotically approaches the formation fluid pressure. So it's valid to assume Carter leakoff at the very beginning of shut in, and then quickly that's not valid. So basically the pre-closure solutions are valid just at the beginning, and the post-closure are valid just at the end. And actually most of the DFIT, the conventional way of analyzing the systems, none of the methods were valid. And so that was kind of the impetus. So I wrote a paper when I was at University of Texas, collaborated with Mukul Sharma there, as well as Ho Jung Jung, who was earning her master's degree at the time. And we did modeling with another fracture simulator where we looked at what happens if you include the effect of the fracture walls touching, and you kind of continuously solve the equations all the way through. And when we first looked at those results, we thought that the simulator must be wrong because we were finding that the conventional method of estimating stress from the DFIT test kept giving the wrong answer. And only upon investigation and thoughtful consideration did we realize that no, we're solving the math correctly, and actually it's some issues with the conventional method. So there was a paper we wrote suggesting that DFIT stress estimates have been systematically inaccurate, since about the last 10 to 15, maybe 20 years. So there's a method called the tangent method, and we find that that's not consistent with our solutions. So then we worked out the math, tried to explain why, et cetera, wrote a paper. So the DFIT study was kind of a follow-on to that. And the question to be asked was, well, what are the implications for everything else? So we had kind of just thrown out there, hey, we think that there's a different way to do the stress, but then there's this whole rest of a workflow in a DFIT analysis where that closure pick goes into all these other things to estimate permeability and estimate the efficiency and so on. And it turns out that if you just change the closure pick and you leave the rest of everything alone, that leads to some pretty weird answers. So you really have to just pretty much throw away what has been done in the past and just build a new procedure. Now, what we built is definitely based on a lot of classical techniques, but there are key changes and key points where we go, oh, that was an issue. So start to finish, we designed a new procedure. It's based on running a huge number of simulations, running simulations that match field data very closely. And then what we wanted to do, though, is create a procedure that could be done by anybody in an Excel spreadsheet. So anybody can read the paper, read the procedure, and implement it using Excel or Python or something like that. So that's what we did. So it's not like you need to run ResFrac to do the DFIT interpretation. ResFrac simulations were largely used to help kind of motivate and understand what's happening, but ultimately it's a procedure anyone can do. So that's what we're presenting in the paper, along with a variety of field data sets. And I'll just also mention some kind of things that have happened since the paper was written. I have a paper coming out in a few months at the International Hydraulic Fracture Technology Conference. We look at 62 DFITs that my company has interpreted for 10 different operators. We statistically summarize them, and really everything that kind of we're predicting in that URTEC paper is consistent with the larger body of observations. So things like what the shape of the transient is supposed to be, how gas versus oil impacts the shape of the transient. So a whole litany of things that we're kind of predicting are bearing out in this larger statistical review. Another thing I'll mention is there was a paper written last year by some scientists in Switzerland where they did some fracturing tests, and they put strain gauges in the rock so they can physically watch the crack opening and closing. That's a way of evaluating basically we run these pressure transient interpretations. We say we think the fracture closed at pressure X, but it would be really nice to have some independent physical measurement of that, right? And what they concluded was that the tangent method, which is the method that we're saying is inaccurate, it in fact was very inaccurate. And there's another data set that hasn't yet been published that I'm co-authoring a paper where a similar type of study was done in South Dakota a few years ago. That paper is going to be put out next year. It shows the same thing, that the tangent method is consistently too low as predicted by the theory and everything else. So anyway, that's a lot. But yeah, that's what the paper is all about. Trying to basically take these ideas, these theoretical findings and empirical findings, and reduce them to a practical engineering procedure. And that is what we have done.
That's really exciting. And I'll probably follow up with you on those other papers that you mentioned, the one that you've written at UT, the International Hydraulic Fracturing Conference paper, and the paper from Switzerland. So
sure.
I will definitely follow up with you on that. You mentioned pretty much in detail in the paper, and you've probably answered part of this question too, but I wanted to talk about a specific part of the workflow. We're all familiar with the G function. Well, those who do their DFITs are all familiar with the G function, but then you're also introducing an H function in the proposed workflow, and I want to know why. And then I know you also mentioned that in this entirety of the workflow, is some of this automated somewhere already?
Yeah, it is. Well, in my company, we have a Python script we use that has automated the workflow. But what needs to happen is the companies that make pressure transient analysis software, they ought to put this into their software. So write them a letter and tell them to, because they're a little bit out of date. But no, there should be. And ResFrac, like my company, we make a fracture simulator. We don't make pressure transient analysis user interfaces. I'm not trying to compete with Harmony, so we haven't invested in that either. Well, actually, what we usually do is our clients, for a pretty nominal fee, we do a DFIT interpretation for our clients. But anyway, and we use our Python script, which we share with people freely. But it's a Python script, so you need somebody who can code to really use it. Let's see, what was your first question? I'm sorry.
Why are we introducing the H function?
Oh yeah, the H function. Yeah. So the H function is a useful mathematical construct for a few of the kind of calculations that are performed. So first thing is to make sure you understand what is the G function and what is its physical interpretation and meaning. So you can go back, the best reference on this, I think, is in the Reservoir Simulation textbook written about 2001. The editors are Economides Nolte, and Nolte is the deriver of the G function from the 70s. So he has a nice section of that textbook where they really do the derivation really nicely. And what they're outlining is that the lowercase, there's two G functions. The lowercase G function is designed so that it is linearly proportional to the volume of fluid that is leaked off from the beginning of injection. And so let's say if you went from little g of 2 to 4, then that means that there's been twice as much fluid leaked off into the formation from the fracture. The capital G is defined as the cumulative being proportional to the cumulative volume of fluid leaked off from the fracture after shut-in. So if you're at a G time of 4, you go to G time of 8, there's been twice as much fluid leaked off into the formation. So that's really useful. And so our procedure uses G function plots. That is a very helpful mathematical construct. The reason that we looked at the H function is because we were looking at estimating the leakoff coefficient. So the leakoff coefficient is how quickly does fluid leak off from the fracture into the formation. And there's, going back to Nolte, you can estimate the leakoff coefficient from the G function, and specifically the derivative of pressure with respect to the G function. Now you have to bring in one other piece of information to close the system, because to do that, you also need to have an estimate for the fracture surface area. And so if you go back to earlier papers, they would do things like they would run a frac simulator, and they would simulate the DFIT with a guess for leak-off coefficient, and then they would iterate. And then there's a really nice paper, I believe it is believe it is Valentin and Economides, who say, well, we don't need to run this is from maybe like the late 90s. We don't need to run a simulator. We can just write down analytic mass balance equations. And you basically ultimately have two equations, two unknowns. You've got mass balance, and then you have this dPdG equation. And then the two unknowns are, roughly speaking, the surface area of the fracture and the leak-off coefficient. So that's a really great method. And what we did is largely to build on that method. But when we look at that method in detail, and specifically, I would run simulations and ask, does this method exactly reproduce the inputs in the simulator? And what I was finding is it was close, but there were some limitations. And so when I looked a little closer at the equation, number one, they neglect wellbore storage. And in a DFIT, if you inject 12 barrels, wellbore storage in your 400 barrel well could be 4 barrels. So you got to include wellbore storage. And they also, on the other side, they made another assumption. So we actually took their equation using the G function and modified it a little bit. So we largely do use that Valentin and Economides technique with a few tweaks to account for two things that they didn't account for that have a non-negligible impact. Then the other problem, though, is kind of with the G function itself. The G function is derived assuming Carter leakoff. And so Carter leakoff, again, that's a classic way of estimating fluid leakoff from a hydraulic fracture, but it assumes that the fluid pressure in that hydraulic fracture is constant. That's a pretty good approximation during propagation. It's a not good approximation during leakoff test when you've shut in and pressure's falling on. And so we said, well, what if could we modify the G function method to include the effect of the pressure fall off in the hydraulic fracture over time in order to account for that? And there's already somebody that's done that. So the so-called Meyerhofer method does account for that. But the H function method is similar to the Meyerhofer method. So they account for it. We make a couple changes. Number one, the Meyerhofer method in their papers isn't like kind of explicitly combined with the Valentin and Economides method. So we kind of combine them together. The other thing is that the Meyerhofer method, it's getting pretty technical, but it uses a time convolution of a rate solution, not a pressure solution. We use the pressure solution because you measure pressure. So doing a time convolution of leakoff rate, but you don't know leakoff rate, potentially makes it less accurate. So also the way the G function is derived is kind of useful in mathematical derivations. And once you've got an H, you just carry around this H, and it kind of is handling a lot of things kind of under the hood. So we define that H function method. It's essentially, I'd say, a little bit of like a combination of the Meyerhofer method, the Valentin and Economides method, our own little tweaks to include things like wellbore storage, kind of mush them all together. and we believe that's the most accurate way to estimate the leakoff coefficient from a DFIT. I found that certainly in comparison with with my numerical simulations. So we run numerical simulations, we compare the methods. H function was doing better. The G function method was doing fine. H function was a little better. I'll add one more thing. There's a third way to estimate permeability, and that's from late time, like the after closure solution, so way later. And there was an open question, is that late time permeability estimate consistent with the permeability implied by the leakoff coefficient? Sorry, my phone is ringing. I will not answer that. And what we show in this upcoming paper is it is. So we look at dozens of DFITs where we have late time estimates of permeability and estimates of permeability from the leakoff coefficient, and they're very close. The H function method, and if you make a cross plot, the H function method is on average 1.5 times higher, so it's 50% higher with a pretty narrow spread. The G function method was on average double and had a wider spread. So my interpretation of that is that obviously the goal is you'd like to get an estimate that's similar to the late time because that's theoretically more accurate. And the H function method is both closer and has less variance. So that's another empirical finding that suggests that while the H function methods, well, the G function method's doing fine, the H function method is, I would say, an incremental improvement over that. But even the G function method we're using is itself an incremental improvement over what Valentin and Economides were doing, because we're accounting for wellbore storage and also the effect of leak off during ejection on the fracture size. So sorry, I'm giving you super long answers, but it's a complicated topic.
It is, and that's why I'm asking complicated questions. I really appreciate that clarification, and I know that our viewers and listeners are going to appreciate that as well, all that information.
And I will say that I just said a lot. I'm sure if you're not familiar with the topic, it would be impossible to follow everything I just said. So you'd have to refer to the papers.
And that's fine. I mean, and that's fine. I've been doing DFITs. I've read some of the literature. I mean, I've read the literature. But I will read the papers. So you talk about, especially with gas reservoirs, and you had the Utica case in terms of the identification of the false radial flow.
Yeah.
I really want to know, how do you know it was false radial flow?
Yeah. The most important novel finding to come out of the study is that there are actually two methods of estimating permeability from DFITs that we believe are extremely high, like 100x too high. And there's been a series of papers we've written on this topic over the last few years. First, false radial flow. I ran DFIT simulations of gas shale, and this is novel. I mean, to use ResFrac is the only way to find this. And so you have to have a combined hydraulic fracture reservoir simulator with multi-phase leakoff, and you have to be handling the fracture closure. Otherwise, you don't find this. But when you run those simulations, what we kept seeing was that you would bend into what appeared to be radial flow very quickly. So you do the DFIT, and then at late time, it looks like radial flow according to kind of a conventional interpretation. Actually, the finding is if you shut in for a really, really, really long time, it would eventually look like linear flow. Mm-hmm. Effectively, what happens is nobody shuts in for a year. And so in the 1 week shut-in period, it looks like radial flow. So that was the modeling finding, and it's related to multi-phase flow effect. Essentially, the filtrate zone has a different viscosity than the reservoir fluid, filtrate zone being the region that's quite thin where water has leaked off into the formation. And that viscosity contrast, as the radius of investigation passes through it, causes a kind of an extra bending down in the transient. But it looks like radial flow, but it is not radial flow, right? So I run a simulation, the pressure plot looks like radial flow, and I look at a 3D movie, it's definitely not radial flow. And that only happens if it's gas in the reservoir, not oil. And specifically, it's the viscosity of the fluid that matters. So that was the modeling finding. And so then we started gathering the data from the companies. And sure enough, in all the gas DFITs that we saw exactly that process. And in my upcoming paper, I review an even larger body of gas shale DFITs and basically show that about 95% of them exhibited, maybe 90% of them exhibited a false radial. Don't quote me on that number, but a very high percentage of them exhibited what looked like an immediate radial, and a very low percentage of the gas shale DFITs exhibited what looked like an immediate radial. And also theoretically, that immediate radial is dubious because a theory predicts it shouldn't happen that early. But if you did take that as radial flow, and then you use the classic equation to estimate permeability from it, what we find is it's about 100 times too high on average. There's another method that also overestimates permeability, and that's a method, I don't know what to call it other than there's Barry is the author who advocates the method. Mm-hmm. So Barry has an equation for estimating permeability from time to closure. Now, first, that's his closure pick. So I actually don't agree with the way he picks closure either. But if we do use his method for picking closure, and we plug into his equation for estimating permeability, he is also arriving. We have in this upcoming paper, I have a histogram, and on average, it's about 200 or 300 times higher than the other methods estimates. And it's as much as more than 1,000 times higher, and it's as little as 3 times higher. So it's always higher, but it's within 3 orders of magnitude of uncertainty. And it's that's an interesting equation. They say it's an empirical fit to data, but then they don't provide any data to show how it was calibrated. And it also is kind of inconsistent with theory. But the main point is that when you take these super high perms in gas shale, and then you run a rate transient analysis matched to production data, they're really high perms. And so the implication is that to make that match the data, the fracture surface area has to be super small. And so you can actually see these authors who are advocating these methods. There's an SPE paper where they say, oh, we've done this workflow on this gas well, and the effective frac length is 30 feet, literally 30 feet. Of course, we know that frac hits go thousands of feet, microseismic goes really far. We can see that wells interfere at wide distances. So it kind of is kind of on its face, pretty remarkable to see anybody claim that the effective fracture length in shale is 30 feet. And they argued something about, well, 99% of the frac doesn't clean out, and so you only produce from the 30 feet closest to the well. And I think that is just an artifact of taking an inaccurate permeability estimation and putting it into a rate transit analysis. So it really all fits together. We wrote another paper. This one was with Hess, looking at their Utica asset, which they've since sold, where we show if you do take the really high permeability estimates, those lead you to really short effective frac length estimates. You end up placing the wells too close together. And you also end up putting the clusters too far apart. So there's really a direct line from these permeability estimates and economic performance. So that's why this is kind of impactful. And really, I think the permeability estimate findings are probably the most important findings from the industry study and that are in the URTEC paper.
Thanks for pointing that out. I think there were several papers in terms of how you can estimate permeability, even though it takes a long time to reach closure for some of these unconventional reservoirs. And yeah, I mean, my personal experience in identifying closure and identifying permeability, my estimates are pretty high myself. So,
well, if you're using a conventional method, it's easy to get that permeability from the test. My experience in a gas shale, it tends to be in the tens of nanodarcies is the permeability that I would expect.
Yeah, the permeability that I've been getting is in the order of microdarcies. So
yeah. Now there are certain formations that are really overpressured that start that way and then they close off really fast. Haynesville is a good example. Okay. So Haynesville DFITs actually can look like they're about 1 microdarcy, and then if you look at an RTA plot, you see kind of a flush early production, and then it drops off hard. And so the way that we have interpreted that in our company is that there actually are relatively open natural fractures. Haynesville is highly overpressured. And then when you draw down the pressure 7,000 PSI, that all closes off, and you go from 1 microdarcy to 20 nanodarcies. And so there's other formations that are gas shales that are more kind of normally pressured or not as overpressured. Those are the formations where you'll see just a nice linear flow trend and you don't see a lot of deviation until you get fracture to fracture interference much later. And those are the formations where you start off at 20 nanodarcy and you stay at 20 nanodarcy. In our Utica paper with Hess, I don't remember the exact number, but we used something on the order of like 15 nanodarcies to match the data. And in that data set, they also had an observation that was really important. They observed outer wells and pads outperforming inner wells consistently, and that was apparent within weeks. And that's only explainable if the fracture lengths are so long that they're overlapping from adjacent wells. And if the effective fracture length is 30 feet, these 900-foot well spacing wells wouldn't be interfering until years later. So you can use interference data to also constrain effective fracture length, and then what you'll find is that fits in with the lower permeability estimate, so it all kind of fits together.
Nice, it's an iterative process. I had another question in terms of a statement that was made in the method section of the paper, and it was talking about how the numerical simulator, that multi-phase flow could also be modeled using black oil. I can understand compositional, and I guess from what I've understood, you can use compositional to model multi-phase, but I wasn't sure how can multi-phase flow be modeled using black oil?
Well, so ResFrac can handle phase behavior using either the black oil model or a compositional model. So like literally in our user interface, you just check a box which one you want to use. And then you have to either put in a black oil table or you have to put in a compositional fluid model, pseudo components, et cetera. So either is fine. The findings we're talking about in the URTEC paper, it doesn't matter whether you use a black oil simulator or a compositional simulator. We're not taking fluid below the saturation point in a DFIT, we're increasing pressure. So really, whether it's an oil reservoir or a gas reservoir, as far as the DFIT is concerned, there's no phase change of a hydrocarbon in response to a DFIT injection, at least as far as I've ever seen. So really, whether or not you use black oil or compositional wouldn't really impact the findings.
Okay, thanks for that. And then I wanted to refer to the Wellbore elements that you talked about in the paper. And I always think about in reservoir simulation, some of the limitations is that you don't necessarily model the wellbore effects, the point at which gas breaks out of solution. So for the wellbore model elements, are you also modeling, like you're predicting pressure losses along a wellbore and when gas breaks out of solution at a certain point in the wellbore?
Yeah, we do a full wellbore model as well. So we mesh the well to the surface. When a well's on production with artificial lift, we will either like literally model the well up to the pump intake, or sometimes we'll just use a bottom hole pressure control. But yeah, we use a full wellbore model, wellbore friction, perforation friction, near wellbore, tortuosity, and that's critical, right? So for our it's important for DFIT because like near wellbore tortuosity is a key part of the DFIT. And general multi-stage hydraulic fracturing, perf efficiency is critical to capture. And so we have to explicitly represent each perf cluster. We have to literally mesh, like you could have the well screen out of the toemost cluster in a stage. And so we are literally meshing the well along that stage so that if the toemost section of the well screens out, then we're blocking off that section of the well and not the rest of the stage. So yeah, we do a full wellbore model. Just think that's critical for accurately capturing realistic processes during fracturing and also during shut-in and production.
I agree. The other question I wanted to ask is, and this is all in relation to DFITs because I am doing DFITs right now at Endeavor, but when describing the types of leak-off, such as the pressure dependent and tip extension, how applicable is that to the rest of the wellbore? Because I know that you end up classifying this as pressure dependent leak-off, your fracture tip extension, but
I think we would all be better off if we just forgot those terms and never used them again.
Okay.
So let me explain why. They arise from this kind of earlier generation of simulations that was performed. So conventionally, what people did was they used frac simulators, and the frac simulators didn't describe closure. And so when the fracture closed, the simulation ended. And I think that kind of introduced what I would perceive as a bias to believing that everything must be a pre-closure process because we can only simulate pre-closure processes. So we will describe everything in that way. The process called fracture height recession, and it's also called transverse storage. That is actually what fracture closure looks like. So if you run a simulation that mathematically solves through the process of closure, when the fracture walls begin to contact, that itself stiffens the system. And so the reason that 2/3 of DFITs exhibit what looks like transverse storage or height recession is because that's what just DFITs do. It's just all DFITs. Now it depends on the permeability. If the permeability is very high, it's qualitatively different. So everything I'm saying right now is relevant to a few microdarcy, maybe 10 microdarcy down. Anything above 10 microdarcy, you're getting into like a different world. Let's not go down that path. We don't have enough. Now the other ones are tip extension and so-called pressure dependent leak off. I'm absolutely open-minded and to the possibility that tip extension occurs after shut-in. In fact, I think that's likely. And also, there's certainly possible that there is some pressure dependent leak off. After all, I was saying earlier that our H function pre-closure permeability estimates come in 50% higher than the late time permeability estimates, and maybe there is some degree of pressure dependent leak off, accelerating that possible. But here's the problem with those interpretations is in a horizontal well, there is near wellbore tortuosity. So the fracture is trying to form at its far field orientation perpendicular to SH-min, but typically the well is drilled in the direction of SH-min. And because of the local concentration of stress around the well, the fracture probably initiates axially, either along the top and bottom in a normal faulting regime or along the sides in a strike slip faulting regime. And then as the fracture gets 5 feet from the well, it needs to rotate completely and have a totally different orientation. And fractures in solid rock don't just cleanly rotate very well. And so it creates the so-called near wellbore tortuosity or complexity, and that creates additional injection pressure. And we have a histogram of that in our upcoming paper. Thousands of PSI is typical. So in the first 20 minutes after shut-in, you can see thousands of PSI of pressure drop. In the Montney, for example, it's strike slip faulting regime up there, 5,000 routine. So tip extension might happen, but if tip extension happens for 20 minutes after shut-in and it's causing some couple hundred PSI impact, and near wellbore tortuosity is also happening during shut-in and it's causing some couple thousand PSI impact, then how could you hope to observe tip extension or PDL in a horizontal well DFIT? So if we were looking at a vertical well DFIT open hole, yeah, you would typically see a little bit of accelerated pressure fall off right after shut-in, which, by the way, there's other interpretations as well, like that could be in the wellbore tortuosity effect or just a little bit of viscous pressure drop in the system along the fracture. But yeah, sure, PDL and tip extension could cause a little bit of accelerated pressure fall off in the early minutes of a shut-in from a vertical well. In a horizontal well, they're at the same time as a much larger and more important effect, which is near wellbore tortuosity. It's basically impossible to see them in the data. And these concepts just get taken way beyond where they ever should have been taken. You see data where people are saying, oh, tip extension happened for the entire 1 week of the shut-in, and you just see things that just really defy reason. And it comes from this kind of literal interpretation of these kind of rather qualitative modeling results in a different context from 30 years ago. It's pretty much what happens.
Awesome. Well, that's good to know. And then you've already touched upon this question, but you also mentioned this in the paper, and you claim this as well. But how do you know those large pressure drops after shut-in are due to fracture tortuosity?
Yeah, that's a great question.
Reorientation.
I really can't wait till my paper comes out. By the way, this new paper was supposed to come out a year ago, but COVID keeps delaying the conference. The best indication is you can compare horizontal and vertical well DFITs. So we have examples in the upcoming paper. In a vertical well DFIT, you don't see it. It's completely unambiguous. So go to a vertical well DFIT, you see maybe a couple hundred PSI of extra pressure drop after shut-in virtually every single time. You go to a horizontal well DFIT, you never see that. So it's crystal clear, and it's an almost perfect pattern. You rarely see anything else.
Okay. And I can't let you go without asking you this question, since I've covered you with a lot of other questions. Some of them are complicated, but from this paper, and I know you've talked a lot about the upcoming paper, I guess what are some applications of the learnings expressed in the paper and that we haven't seen before in this industry?
So we're recommending a different stress method of estimation. It's usually only a few hundred PSI different, but the net pressure estimate, which has direct implication to fracture size, is usually like double or triple different. So it's usually half or 2/3 smaller in our method. So that's a big change. The permeability estimates, it's an incremental improvement over some permeability methods, but it's also identifying other permeability methods that can be drastically inaccurate and lead to kind of suboptimal well spacing, for example. For me personally, I kind of like the theory. Like I think we've set up a ton of new theory that others could build upon, and there's a lot of opportunity to do more with DFITs and extend these methods. And I hope that others in the field pick it up, because I think there's a lot of interesting new things theoretically laid out.
Awesome. Well, I'll be sure to use this workflow because I've been reinterpreting some of our DFITs, and I've looked at this paper, and that's why I was really interested to know if this has already been automated, so I could just see some diagnostic plots already without having.
I'm happy to send you our Python script if you like Python.
Oh yeah, I do like Python.
Okay.
Well, Mark, I really appreciate you taking the time to letting me pepper you with questions on this podcast. And that is all, viewers and listeners. You heard it straight from Mark. Make sure you check out the paper, URTEC 123, as well as the other papers that we referenced in this podcast. I'm Yogeshri Pradhan, and I'm signing off.